So welcome at session six. Welcome at session six. In this session, we will learn about some neural network architectures, some variant of architectures. We have seen only the feed-forward and the perceptron architectures so far, but there are many, as I said. And today we will talk about the basic 5 architectures, actually 6 architecture, and the rest of the new architectures actually they are kind of child of these architectures or diverse from these architectures. So as I said, many neural network architectures have been introduced in the past decade. Actually, every month there could new one come. The main motivation behind proposing new architecture are, first of all, overcoming classical learning problems like generalization, like overfitting, gradient vanishing, explosion, overfitting, and so on. But also dealing with a new task like we need to build a neural network to fit with natural language processing. That means we need to adopt some of the architectures, and then we end up with new architectures. New learning techniques, for example, like reinforcement learning or generative adversarial networks, this also led to, we'll see what the meaning of that, this also led to new network or deep learning architectures. Starting with the first one, which is the simplest one that we have seen, it's the perceptron network. Using binary classification, it deals only with single neurons, so it's not multi-neuron, not multi-layers. It uses a perceptron learning that we have seen in the second lecture. So here we see basically just an input, 2 neurons, and here we have the output neuron. And using the perceptron, we learn the weights actually that connecting this neuron with the neurons before. Feed-forward neural network. We have seen also. It is similar to perceptron, but now we can have multi-neurons, we can have multi-layers, multi-hidden layers. Feed-forward, as I said, basically the knowledge or the information propagate from the inputs to the output without any recurrent connections. It could have multi-neuron, multi-layers. It's used for binary or multi-class classification. It's used for regression. It mainly uses backpropagation to learn the weights or to learn the task. So here we have in green the hidden layer, the output layer here in orange, and in yellow we have the input layer. So here I have 2 examples of the feed-forward neural network. One is when it comes to classification. Let's say we have 3 classification problem and or task. We are using 2 hidden layers. That's why we have 2 green here layers. And we have basically 2 neurons actually per hidden layer. We have 3 inputs. That means we have 3 features like colors, shape, size. And we have 3 classes. As I said in the lecture before, the number of outputs should always be equal to the number of classes. So we have 3 outputs. And when it comes to multi-class classifications, bigger than 2, bigger than binary, then we need to use softmax there as an output. It's very common to use, as I said also in the lecture before, ReLU function in the hidden layers. So during the learning, during the backpropagation, we are learning all the weight connections between all these neurons like we see here. It's fully connected feed-forward network. That means, again, each neuron in layer L2, for example, are connected to all neurons from layer L1. Same here and same here. Now, if you talk about regression now, let's say that we're trying to predict 3 values, 3 continuous values, temperature, humidity, and something else, for example. These are continuous values that we are trying to predict. It would have the same architecture like the classification. The number of outputs would be equal to the number of variables that we're trying to predict. But usually, instead of using softmax, we use linear. Actually, we never use softmax for regression. This is just to know. We use linear, or sometimes they use sigmoid when the data is scaled between 0 and 1. But I don't recommend that. Use linear always. And of course, the hidden layers could be ReLU, sigmoid, or whatever, but always recommended to use also ReLU or one of the childs like ILU or Leaky and so on. Now another architecture was proposed to deal with sequential or temporal data. Sequential means that we have basically sequential inputs like text. Text has words, and words comes sequentially, so they have sequential relationship. Time series, for example, temperature is temporal, also sequential mainly. That means we have, for example, the temperature of yesterday, the temperature of today, the temperature of tomorrow. They are sequential inputs, so basically time variant inputs. Once it comes to sequential or time variant inputs, we need to use, or it's recommended to use, recurrent neural network. What the idea of recurrent neural network is that hidden neurons, they have recurrent connection to the neuron itself. How that mathematically look like? We have seen that we have the pre-activation before. So this is the activation function. This is a pre-activation where we multiply the weight with the input from the neuron before, plus the second weight with the input from the second neuron in the layer before. Now plus third weight here, which is the recurrent weight, multiplied by the activation of this neuron at time t equals 0. So if we are now at time t equal 1, which let's say is today, we are taking the output of this neuron, the historical output of this neuron, at time t equals 0, let's say it's yesterday. So this is basically, the neurons always store its recent output and use this recent output again in the model to predict the current value. Okay, this is the idea of recurrent neural network. It could also have multi-neurons, multi-layers. It used backpropagation, can be used for classification, and can be used also for regression. It has many, let's say, models that diverged from recurrent neural network. I will talk about them later. One is called LSTM, and one is called GRU. They are basically gated networks, they're called. They are recurrent neural networks, but they can have what is called long-term and short-term memory. This is a short-term memory because we only storing what happened in the step before. Long-term memory is basically if I want to include what happened a month ago in my decision for tomorrow. So it's basically, this is long-term and short-term memory. There is a recursive neural network, which is similar as recurrent. Sometimes it's combined with recurrent. But here, basically, the output of the output layer of the output neuron is considered in, or actually is used as additional input to our neural network. So the difference between recurrent, the hidden neurons, they have connection with their own history. Recursive, the hidden neurons, they have connection from the output or from the history of the output neuron, the history of the whole model itself. It's also used for sequential, it's also used for time series, and as I said, sometimes combined with recurrent neural network. Now another architecture which is very interesting, and we will see it also in separate lecture later. It's called the autoencoders. The main goal of autoencoder is basically to do dimension reduction and to do representation learning. What the meaning of dimension reduction? First, we have an input here. We have three inputs. We have three features. And we have seen that we reduce the dimension to 2, then to 1. Each neuron here has one output, we know. And the neuron, basically one output, then if that means if I have one neuron in that layer, I have only one dimension. If I have two neurons in that layer, that means I have 2 dimensions. If I have 3, that means I have 3 dimensions. Now, the idea of dimension reduction is basically to build useful representation of the data. Let's say we have an image here with 1,000 pixels, or actually million pixels. Then not all these 1 million pixels are important for me to analyze this image, let's say to detect lanes or to detect pedestrians, because there are many background objects that I don't care about and I only need to concentrate on the pedestrians themselves. So what happens here in the dimension reduction, this basically autoencoder can squashing the information until it reaches here a useful representation. We will see an example later. The dimension is much lower. Here we have only one, actually, one vector. that we can use to actually decide. So what is interesting about the autoencoder is the way it learns that representation. So the way it learns that representation is actually by reversing the process. So we have seen here, this is the input. We actually squashed, which is basically just called the encoding area or the encoding phase. We squash the information until we reach here, the latent space it's called, or the representation space here. Then from there, so this is forward propagation, just remember. That means the information will propagate until here, then it will propagate until the output, then here we can calculate the cost, and then from here we can back propagate. So we forward propagate. We have here, for example, the representation. Now the challenge is, can I predict again the same inputs from that representation? Having said that, the inputs values here and my targets here are the same, which means if I have here color, shape, size, I would here also have color, shape, size. And the idea here that the model after it reduce the dimension to 1 and then predict again the output from that one representation. The predicted output should be the same as my input. This is why autoencoder is unsupervised learning, because it doesn't require labels. It doesn't it's not classification or regression. It takes your input features and try to predict them again by building a representation of these features. So I'll just explain that in the next example. But here it's basically a feed-forward network. The only difference is that we are squashing the knowledge, so we are actually reducing the number of neurons when we go until the latent space. Then we start to increase the number of neurons until we get again to the same number of neurons as the input. It could have multi-neurons, multi-layers again, and your back propagation. So what's the meaning of better representation? Let's say we have let's say we have 3 neurons here, or 3 features at the input. This is my data. It's basically, I cannot split this data from each other. I cannot do now classification or something. I need to reduce the dimension. I need to remove the redundant information, or actually the noise from this data, and I need to end up with better representation. So what happens here, the autoencoder will squash and try to extract important features here until it reaches a better representation, where the red points are on the left side and the blue points are on the right side. Then, for example, we can do here classification easily in the latent space, because we could actually split them by a single line. Then, of course, if the autoencoder learns that good, if I have here this red point here, it will actually go through the autoencoder, then it will be projected on this region. And then from this region, if we go continue again, it will be basically predicted again in the same position. This is called encoding decoding. Another example to understand this, that this is very basically high abstract example. Let's say we have features like there is an accident. It's features about a story or about a scene, that there is an accident. People are cutting or they have umbrella open, and there is traffic jam. Now this is our data set. Sometimes we would have accidents without umbrella. Sometimes we have it basically together. Sometimes, so this is basically kind of a combination between these 3 features, and we have many scenarios. Now, let's say that the first neuron in the first hidden layer would learn something about that scene. Would learn that if let's say, the road is wet or not. Yeah, so it would kind of inference something about the scene from what it sees. Let's say if it sees like umbrella and accident, then it would, let's say, assume or predict that probably the road is wet. It would also predict another neuron, as I said, each neuron learns specific task, specific feature. Another neuron would say, I'm seeing it's probably unclear vision. Now the third representation would be, okay, if it's wet and unclear vision, then here the high abstract meaning of that, it's raining, or there's rain. If we go in the other direction, we can see this is the causal model, it's called. If it rains, that means it's the road, of course, or the road would be wet. We would have unclear vision. Wet roads would lead to like an accident. Also would lead to people, or it cause here in this case, people carrying umbrella. It would also cause probably traffic jam. Unclear vision also would cause all the three. So this is the meaning of representation. From scene, we can build a higher representation. And from this higher representation, we probably could predict the same scene again. For example, from the same data, let's say this is the red part where we have rain. So this is basically the region or the data set of rain. Then on the right side, we have another, for example, which is the clear. Clear here, if the weather is clear, that means probably the road is dry. That means probably we have a clear vision. That means probably we have no accident, no umbrella, and probably we will also have traffic jam. So maybe traffic jam here is redundant as uncaused by any of this. So, and here the encode basically would have the opposite. So if there is no accident, no umbrella, even if we have traffic jam, this should be dry. So this actually should be dry here and clear vision. I'll correct it now in the PDF. So dry and clear vision. And that means here we have a clear also scene or clear environment. So this basically should be always opposite of the, so the decoder is always opposite of the encoder. I mean here, this information, abstract information that I put there, these are, let's say, human-made features that are extracted. But this is a power of your network, the power of the autoencoder. You just need to provide this autoencoder with input data, which could be high dimension, like we see here. Could have noise inside, could have a lot of redundant information. It would squash it to build high-level representation, like we have seen here. Like, is it only high-level representation, only raining? Is it wet? Is it unclear? This high-level representation. And we'll use this higher-level representation to predict the output. Another example of autoencoders we could see basically now what's called deepfake. And deepfake, it generates human-like faces. They are not real faces, but they are human-like faces. So what happened there, how they train such systems, we'll see GANs later, but for example, autoencoder also could be used for that. We take input images, a data set of human face images. Then, for example, we feed these images to that autoencoder. So here at the input, we would have, let's say the images, they have 100 pixels. So we would have here 100 inputs. Then we will start to reduce the dimensionality until we end up, let's say, with four latent space. So the latent space is not necessarily always be one neuron. It could be 4, it could be 5, but it's clearly is much less than the input. Because the input here we have, let's say, 1000 pixels. We end up with 4 pixels at the latent space. These 4 pixels in the latent space could represent now high abstract features of the face. This face, for example, the color of the face, the color of the eyes, the color of the hair. Let's say this is 30 neuron. And for example, for example, the gender. So we have these 4 features. They are represented in these 4 neurons, would be represented the 4 neurons in the latent space. Now, using these 4 neurons, I can predict again how the face looks like. So now when it comes to generating new images, I can manipulate, which means move the values along the axis here in these 4 neurons, manipulate them and try to generate again new faces. And this is the idea of the autoencoder, this idea of the representation layer, high level representation layer. For example, we represented human faces or human face images with only 4 neurons that represent 4 distinct features like color, hair color, for example, eye colors, and also the gender. These are 4 features. Now, another type of neural network, which is very famous now as well, it's feed-forward, or also could be now with convolutional, as we'll see later. It targets, this new architecture targets one of the challenges that we have seen. It's called the gradient vanishing. And it's also it smooth the cost function at the end, as we'll see later. But the idea of gradient vanishing that we have seen, basically, if we are doing multiplication, then the knowledge could vanish. The residual here network, or the idea here basically is just to introduce new skip connections, they are called, which basically connect a neuron, for example, at layer 1 with the neurons at layer L, or let's say this is L plus 2. So we are skipping the intermediate layer. By doing this skips multiple times when it comes to really deep networks, so residual here actually works better when we have really deep networks. Deep networks, I mean now we have networks with 100 layers. And that basically would make the propagation of the gradient or backpropagation better, because even if the gradient could vanish here, we still have kind of skipping that connection there, just to make sure that the gradient doesn't vanish. So we see it basically here again in the model. So now the output of the A4, this one, because this is 1, 2, 3, 4. The first neuron at the layer 4 is equal to the function now the weighted sum of these two. So this is actually the 2 neurons at layer 3, but also we have the output of the neurons at layer 1. So this is basically the skipping of the connections, and we will do that, of course, for all neurons in this layer. That would also repeat if we have a deeper network. The idea of skipping connections is to avoid gradient vanishing. It could be applied to classification, regression, could be applied with autoencoders as well, with recurrent neural networks. So this skipping connection is just an idea of how to improve the learning, how to avoid gradient vanishing, and which leads at the end to better performance. So this is just the gradient vanishing, just to understand what is it solving. As I said, so this idea, instead of basically going through all the neurons, it will still go from neuron to the other, but we have skip connections just to send this gradient from the output neurons, for example, directly to this neuron, and this way we avoid the vanishing problem. So this is a summary of the 6 architectures that we have seen now. We have the perceptron, which is the simplest one. That has 1 neuron that uses the perceptron algorithm to learn. Feed-forward network could have multi-layers, multi-hidden neurons. It could be used for classification and regression, and mainly use backpropagation. Autoencoder is a kind of feed-forward neural network, but has the idea of squashing, which means building the representation and reduce the dimension at the latent space here, or the representation layer. It is unsupervised learning, which means the inputs here and the outputs, they are the same. What we are trying to do is to reduce the dimensionality and again predict the same inputs. The target here to have a representation of that input, so correct representation. We have recursive and recurrent. They are both used for sequential and temporal data sets, or time invariant data sets, for example. And the idea here for recurrent, we have a recurrent connection from the neuron to itself. The idea under recursive, we have recurrent connection from the output neuron to the input neurons, or to the hidden layers as well. And we have the residual, the idea here to skip the connections to avoid gradient vanishing problems, so to add skipping connection between neurons and deeper layers. So thank you very much, and in the next lecture we'll talk now about more fundamental of neural networks. We'll talk about loss functions, we'll talk about also visualizations, and also some other tricks in your network before we move to cellular neural not cellular, sorry, convolutional neural network, which is called the CNN, which is a specific type of neural network that is used for machine vision. Thank you.